In this video, we'll take a look at how to prove statements that involve two different types of quantifiers, or in general, many types of quantifiers can extend from what I'm about to tell you. So what I mean by this is, suppose we want to prove a statement like, for all x in S, there exists y in S, or maybe a different set, such that R of x, y. Right, so this is going to involve sort of two different kinds of proof techniques here. One, because we have a universal statement, so my x here needs to be arbitrary. I'm given just this arbitrary element of the set S, and then I need to use an existence proof. I need to show that there exists some y that can be based off of x. I'll note that can be based off of x. That is, it can be a function of x, such that R of xy is true. So there's one type of statement we'd like to be able to prove, and then the other is if I switch the order of these. So suppose I also want to prove a statement like there exists x in S, such that for all y in S, R of xy. And again, maybe these two sets are different, maybe they're not. So here I need to come up with an example, of x in S, and show that for any, so this would be now an arbitrary element of S, for any y in S, R of xy. So notice the difference between proving a statement like this and proving a statement up here. Here, my order would be let x be in S. So this is an arbitrary element of S. And then using that, come up with an example of y in S such that R of xy. So the order here is different in terms of the existence and the universal statement. And so the proof techniques are different in each case. So what we're going to do is we're going to look at an example of each of these. And hopefully you'll see how these are different and be able to extend this to other problems. All right, let's take a look. So result 3.40 says for every rational number S, there exists for every irrational number S, there exists a rational number R such that Rs is irrational. So this is an example of a there exists and then a for all statement. Or sorry, other way around. For every, so this is a for all irrational numbers S, there exists a rational number R. So that is for all S in, I'll say Q complement. So universal set is the real numbers here. I'm using this complement. For all irrational numbers S, there exists a rational number R such that Rs is irrational. So to start this, my initial assumption is that S is an irrational number. So let S be irrational. And now I need to come up with an example of a rational number such that when I multiply it by S, I remain irrational. That is, the product is still irrational. So how can I guarantee this? What if I was given something like, how can I guarantee this? S could be, say, square root of 2, or S could be pi. How can I come up with a rational number in any case and still end up with the product being irrational? Well, the idea is to not change it at all. S is irrational, and so if I can make my product just S, then I know S is irrational, and so this will be accomplished. So the idea is to choose R equal to 1. Then when I multiply by S, that's still equal to S, and that'll give me what I want. So let S be irrational, and let X let R equal 1. Then R times S is equal to just S, since R is 1, which is irrational. And that proves it. So no matter what irrational number you give me, I can find a rational number such that their product is irrational. Let's look at an example of the other situation. So here we have there exists a rational number, R, so R in the rationals, such that for all irrational numbers, R times S is rational. Now this one might seem a little bit more difficult. So I'm given just a rational number, and I want to show, or sorry, I'm not given a rational number. I need to come up with a rational number such that no matter what irrational number I throw at it, the product is still rational. So, right, for instance, what if I thought maybe R equal to 1 would work here? I could then pick S equal to square root of 2, right? That's an irrational number. What if S is equal to square root of 2? And then their product would be square root of 2. That would be irrational. So R equals 1 won't work here. So I need to do a little bit more thinking of a special rational number such that no matter what irrational number I multiply it by, the result is still rational. You can pause here if you want and think about it for yourself for a little bit. Otherwise, I'm just going to give away the solution here. So proof, let R equal 0. Then R is rational. And for any S in the irrationals, so notice here my S is arbitrary. I don't get to decide on what S is. I have to show that this works for any S. We have R times S is equal to 0 times S is equal to 0, which is rational. And that proves it. So again, one thing to focus on here is what is arbitrary in each of these. What am I using like as a variable, and what am I getting to decide? For this exist thing, I decide on the R first, and then I show that no matter what irrational number I'm given, right, my S here is just S, the result is rational. In this case, I let S, right, S was arbitrary and given first, and I came up with my rational number after that fact, after it had been established that S was an arbitrary irrational number. Okay, that's it for this video, and that's it for this week. I'll see you next week.